Earth calling thermo class. Earth calling thermo class. Come in thermo class. Seem to be having trouble here. Okay. All right. Monday, June 15th. Thermo. Do we have anybody that's showing up for class? Nope, we don't. Well, maybe they'll show up. It's only 8:20. So we'll just patiently wait. I think I don't have any customers yet, but I think I'm doing okay.
Yeah. Nobody's on yet.
They're just not on yet. They'll show up. Bye. Well, we're waiting for customers here. Yeah. Okay, participants. Well, I hope somebody shows up. Well, let's think about what we're going to study today. We're in chapter 3, I know. And we're waiting for people to show up. Well, I've got 8:25. Class starts at 8:30. Where is everybody? Let's see what we're going to study today. We're going to study we'll have some topics here. We'll have that topic. Maybe well, there's two pretty good topics right there, and we could work those over. Well, what if nobody shows up? Oh, there's a customer right there. There's Spencer. Always faithful Spencer. He's showing up. Hey, Spencer.
Hello, how are you?
Not too bad, considering it's Monday morning. We don't have any other customers, though. Let me see if I can find some more. Okay, now what's the secret here to get the full screen? There's some kind of secret here. I wonder what that little blue thing is. Oh, there it is. Now I've got a full screen. Let's see if we got any more participants. Oh, yeah, we've got Aubrey, Cameron, Spencer. Well, and with me, that's 4 of us. All right. We're coming right along. Okay, class hasn't officially started, but any of you have a comment or question for me? Did y'all get your grade on your test? You should have. I graded some tests. I've got them in my grade book.
It shows up in the final grade, but it doesn't show us what our actual grade on the exam was.
Yeah.
Oh, really? Really?
Yeah,
Well,
it's
that's
part of the
weird.
total, but not its own separate thing.
Oh, really? Well, thanks for telling me that. I'll check on that. It doesn't tell you what your test grade was. Okay, well, we'll figure it out. Hey, there's Parker. I've got another. Yeah, there's another student. And there's Stuart. Yeah, welcome. Any other, that was an interesting comment, and I'll check on that. Any other comments or questions on anything?
I missed the last lecture. When will it be uploaded to YouTube so I can watch it?
Gee, it's not loaded yet?
No, I don't think so. I checked last night.
Okay. that would be the last Wednesday's lecture.
Yeah.
Well, it should be loaded. Let me check on that. We'll figure that out, hopefully. Thank you for
Okay.
telling me that. Anybody else have a comment or question? Okay, well, we'll go ahead then. The topics today are delta little h, which is, let me get this out of the way here. You probably can't see this. There, but you can see this. You can see this delta little h, and that's the change in specific enthalpy. And that's our topic. And then we'll study polytropic processes. Those are two big topics for today. There's 4 ways you can do this. And let me show you the 4 ways we can do this. There's an example in your book showing you this. It's example 313. In my book, it's on page 94. But they do this 3 different ways. And one way is they just look up these values in the table. Now, this particular problem is oxygen. So they're dealing with molecular oxygen. So you have to go back here in the back and find an oxygen table. Let me shop around here. There's one on, it's table A13. Well, no, I guess it's page A13 in the appendix. It's table A.8. Now, what they've got there in this problem is oxygen, and it's going from 300 to 1500 K. Okay. Oxygen is going from 300 K to 1500 K. And so what you do is you write down the oxygen for 1500 K, which is, you write down the specific enthalpy, I mean, it's 1680.70. 1680.70 kilojoules per kilogram. They're treating oxygen as an ideal gas. In ideal gases, the specific internal energy is a function of temperature alone, and the specific enthalpy is a function of temperature alone. And so we don't care what the pressure is. It doesn't matter. It's an ideal gas. So you just take H2 minus H1. Now what's H1? At 300, it is, for oxygen, 273.15. Now, I need you guys to find those numbers so you'll know where on earth did he get these numbers? Well, I got them from table A.8. Can you thumb through your computer there and find table A.8? Can you do it?
I believe that 1680.70 is for nitrogen, not oxygen.
Oh, I appreciate your help. I appreciate your help. It's no, I'm getting 273.15. Oh, you're talking about the 16. All right, I'm with you. Just a minute. That's not right. Thank you so very much. You're absolutely right. It's 1540.23. See, it's so easy to teach good students that pay attention and are awake. There, I have it. I have it right now. Now, who was that just helped me? Was that Spencer?
That was Stewart.
Stuart, thank you. Stuart, I'm going to put a thank you point up here in the corner. See that there, Stuart? That's your thank you point. Good going, Stuart. And you helped the class. Now, I want to make sure y'all can find that. Notice I did a little Southern talk there. Y'all, can y'all find that? I want this here and that. Can you find it? I know Stuart can because he just helped me on it. But I need somebody else to say,
I found it too.
Yay, good going. Now who was that?
Spencer.
Spencer, good going, Spencer. Okay, well, now that's one way to do it. Now we're going to do it another way. We're talking about oxygen, molecular oxygen. And now we're going to do it a different way. Now, what we're doing is we're going from 300K to 1500K. I just need this room here, so I'm going to erase that. We did it with table A.8. And now we're going to do it a different way. Now, another way to do it is you could actually integrate it. There's a function, and it is on page, let me see if I can find this. Yeah, there it is. It's table A6. And there's a function, see, delta H is equal to the integral of C sub P dt. And they have a function there for oxygen. Let me find it. There it is. And it goes like this. 0.88 minus 0.0001 theta plus 0.54 theta squared minus 0.33 theta cubed d theta from theta 1 to theta 2. Now, I want you to go to table A6. In my book, it's on page A10. And I want you to see if you can find these numbers. Did I get them written down right? I need Stuart to help me on that for oxygen. I think I did those right. Can you find those?
Yes.
Yay, good going. Okay, now if you look at that table though, I lost my place. They said theta is equal to your absolute temperature divided by 1,000. Up there at the kind of at the top of that table, That's what they say. See, they changed the variables. See, this here should go from T1 to T2, but they changed the variables on you. So what you'd have here for theta 1, instead of 300, it would be 0.3. And here theta 2, instead of 1500, it would be 1.5. See, this T1 is 300K, and this T2 is 1500K. And there we go. And but when you divide by 1,000, they're changing the variables. Now, here's a tricky thing here. They've got a d theta here, but this is a dt. Well, we're going to do some calculus now. D theta should equal dt divided by 1,000. Can you math people get from here to here? Can you make it? I think so. Okay. So see this dt, see if you can get to here. dt is equal to 1,000 d theta. Can you get from here to here? Well, you're going to have to put 1,000 d theta in here. Now, that was wrong what I had there. This is correct, but dt is equal to 1,000 d theta. See, here's your CP. I did that right. And your dt is 1,000 d theta, and I did that. Now we're going to integrate that. Now this is the second way of getting our change in specific enthalpy. We did it this way here, and now we're doing it by integrating this empirical function. Empirical is just a fancy word for derived from experiment. Okay, here goes. I'm going to integrate it now. Well, I'm getting delta H is equal to 0.88 theta minus point blah, 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 theta squared. Watch it, theta squared over 2, right? Plus 0.54 theta cubed over 3 minus 0.33 theta to the 4th over 4. But now wait a minute, there's 1,000 there. So I'm going to have to multiply this whole thing by 1,000. dH is equal to 1,000 times all this stuff. Now, for anybody out there that tuned in late, we are doing example 313. It's on page 94 in my book. And it's a way of calculating the change in specific enthalpy. You can read that. Okay, now what we're going to do is we're going to plug in these values from 0.3 to 1.5. All right, I'm going to get my calculator now. And I'm going to plug in, I think what I'm going to do is step by step. I'll go 1,000. And then I'm going to plug in the 1.5. Here I go. I hope some of you are following along with me here. Minus 0.0001 divided by 2 times 1.5 squared plus 0.54 divided by 3 times 1.5 cubed minus 0.33 divided by 4 times 1.5 to the 4th Well, what I got for all that stuff when I plugged in 1.5, I got this here. Now I'm going to have to plug in the 0.3. All right, well, here goes. I'm going to plug in. See, I plugged in the 1.5. Now I'm going to plug in the, I should have written that down here, huh? The 0.3 and the 1.5. Yeah, there we go. Now I'm going to plug in that 0.3. Here goes. 0.88 times 0.3 minus 0.0001 divided by 2 times 0.3 squared. 0.54 divided by 3 times 0.3 cubed minus 0.33 divided by 4 times 0.3 to the fourth. I'm getting 0.268, blah, blah, blah. And now I'm going to subtract those and multiply by 1,000. Okay, here goes. Plus 1.5097 times 1,000 equals, I'm getting 1241.5 kilojoules per kilogram. Okay. Well, what did we get? Oh man, that's not very good. That is not, maybe I made a mistake. Let me see what they did. Maybe I made a mistake.
Did you
No,
square
no.
everything instead of just squaring the theta values?
Uh-huh.
Like when you raise them to the exponents, like to the second, to the third, to the fourth, did you accidentally raise everything instead of just the thetas?
Just the thetas. You know how to integrate. They got a different answer, guys. They got the 1292. I got 1241. Okay. Just a minute here. No. That's what they got. No, I did it right, guys. If you'll look on example 313 on page 94, they got 1241.5. We agree. I did it great. Now, when they subtracted these, did I ever get that answer? When they subtracted those? I don't know. Maybe I didn't write it down. Let me get this answer when you subtract those. And what you get is 1540.23 minus 273.15. 1267.08. Well, that's what they got. They just rounded it off there. Okay. Well, we've got two of the answers they got. We agree with them. All right. Well, there's two ways to do it. Now we're going to do it a third and fourth method. This is kind of tedious and took a while, but we're integrating. Now this up here, what they've done is they've integrated for us already. Now, why these didn't come out precisely the same, I don't know. I don't know why they didn't come out the same, but they're pretty close. What are we off here by about 27 out of 1,200? That's not too bad. Let's see, 27 out of 1,200. 2%. We're off by 2%. But what these things are here are ideal gas integrals. They have integrated this function here, this empirical function, and now we have we have that value. So let me erase all this stuff and put the answers in there, and then we'll do it a couple other ways. You could always read the book. That's another thing. We got 12, 41.5 kilojoules per kilogram. We have two answers now, this one here and this one here. Now we're going to do it another way. I'm going to erase all this. You guys should read the book. They do it in the book. Here we'll number these. This is method 1, method 2. Now method 3 is a very bad method. They're using well, let me read this and see if that's what they did. Just a second here. Yeah, I think so. Method 3 is going to be an unhappy method. We'll put an unhappy face here. What they did is they just did this here. And they used the specific heat at room temperature. Well, it's going to give us a bad answer because when you go from 300K to 1500K, that's not room temperature. I mean, 1500K, I don't know if steel will melt at that temperature. We'd have to look that up, but that's pretty dang hot. But what they did was they just looked up the C sub P at room temperature. Let me see if I can find that. It's, we're doing oxygen, remember. We are doing oxygen, molecular oxygen going from 300 to 1500. And C sub P at room temperature is at 0.922. You can find this on table A.5. Go to table A.5 and you will find it. Now the units are kilojoules per kilogram Kelvin. Now the change in temperature going from 1500, that's the final minus the initial. You will get your change in specific enthalpy. Well, here goes. We're going to get it. This is a third method, and this is not a very good method because our temperature is not room temperature. Okay, 1500 minus 300. Okay, well, I got an answer. I got 1106.4 kilojoules per kilogram. Is that what they got? That's precisely what they got. I'm doing everything correct here. Now notice these two are pretty close. They're off by about 2%, but this is way off. Let me see how much it's off. 1106. Oh, this answer here is off by about 12%. Well, that's not very good. These two answers here are off by 2%. That's pretty decent. But now there's a fourth method, and this fourth method I kind of like. I'm going to put a happy face on it. I don't like this method because remember this one, you have to integrate this big long thing. And there's a whole bunch of numbers and it takes a while. That's kind of, I like this one. Here, I'll put a happy face on this one. You just look them up. They've already integrated for you. Isn't that nice? But now this is a nice method too. Now what they did here, they got an average C sub P. They said the change in specific enthalpy is equal to this average C sub P dt. Now, how are we going to get the average C sub P? Well, we're going to go back to that fancy-wancy empirical equation. And we're going to find the average C sub P. Now, first of all, we got to get the average temperature. Well, between 300 and 1500, you know what the average temperature would be? I can do that in my head, I think. Wouldn't it be 900? Wouldn't the average temperature between 300 and 1500 be 900? I need somebody to say, uh-huh. That's the average temperature, right? Between 300 and 1500?
Yeah.
Yeah, I heard a yeah. So, so what? Well, we're going to use that table and find the average C sub P. I'm running out of room here. But we all know it's Monday, June the 15th, right? I don't need that. We'll say goodbye to that. It's Monday. And the topics, we don't need that. We know we're doing finding the change. We're finding the change in specific specific enthalpy by 4 different methods. And right now we're going to get the average. I put a bar over it to denote the average. Okay, here goes. For oxygen, I'm back to table A6. Go to table A.6. And you go, this is a little bit tedious, but not bad. I don't mind it too much. You go 0.88. No, it's minus 0.0001 times theta. But now wait a minute. Theta, remember, is going to be the 900 divided by 1,000, so it'd be 0.9. I skipped a step. I hope you're with me. And then I have to go plus 0.54 times theta squared. Well, theta is going to be 0.9. And then you go minus 0.33 theta cubed. That'd be 0.9 cubed. Did I lose anybody? Anybody need help on that? I'm using table A.6. I'm finding the average C sub P. They call that specific heat. Anybody need help on that? Are you okay? Well, I'm going to put that in my calculator. Here we go, 0.88 minus 0.0001 times 0.9 plus 0.54, 0.9 squared minus 0.33 times 0.9. Whoops, I just screwed up. But maybe I did it right. I'm getting 1.07674. I wonder if I did that right.
That's what I got.
I bet it's right. Thank you. Okay, and now what we're going to do is we're going to say delta H. Well, I have it down here. See it? I have it down here. This is our 4th method. We're going to say delta H is this average specific heat, which we think, if I did that right, is 1076 blah, 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 times the 1500 minus 300. I'm going to do that. Okay, here goes. Times 1500 minus 300. Well, I got an answer. I'm getting 1292 kilojoules per kilogram. Now let's see what they got. Uh-oh, I lost my place. This is example 3 something. 313. Maybe I can find it here. I got lost. Example 313. I'm getting close. Okay, 313. By Jove. Anybody know what page it's on? I got lost there. There it is. Okay, now they did it and they got 1292. Hey, Shazam, look at that. Look at us. We got what they got. Now I want you to notice that this is pretty darn good. This is 1292. That's not terribly off of the 1267 or the 1241. All three of these kind of in the ballpark there, aren't they? This one's fairly easy to come by. But of all of these, which one is the easiest? Well, it's this one. They've already integrated these for you. These are called ideal gas integrals, is what they're called. That's the name of them. And now I've shown you how to get delta H 4 different ways. And maybe you understand a little better. And we'll move on to our next topic. Probably ought to do a problem on that, though. Well, we'll do some problems and we'll use that here in a little while. Okay. Up to you. You can ask me anything or we're going to move on to the next topic. That topic is how to figure delta H. Why do we care anyway? What good is delta H? I told you the main use of delta H the other day. I can't figure out why I have a small picture of me up here in the corner. Show grid video. Show thumbnail video. Oh, I just got a picture of Spencer and Parker there. That's cool. Maybe I should just leave that alone. Okay. Well, I'm going to erase all this and I'm going to tell you why we care. Okay, there it goes. If you didn't understand any of this, you could read example 313. But of the 3 methods, this is the worst. This here you don't want to do. It takes forever. You got to integrate a big old long thing. You don't want to do that. These 2 are pretty good. This is the way to go. You just look it up. Okay. Well, I'm going to make some room here so I can talk to you. All right. Now, what we've just been talking about is how to figure the change in specific enthalpy. And I think I told you why we care. Let me find a pen that writes better. Well, that one's okay, I guess. Let's try this other one. But why do we care about delta little h? Here, let me pick on somebody here. Let's see. We'll come down here. I always I always start with my friend, well, I don't know, Parker's right there. Parker, why do we care? What do we want to know what delta H is, Parker?
I don't know.
Good. That's a good. I love honesty. Well, here I'll just tell you. We have many isobaric processes in this class. If you have an isobaric process, it really doesn't matter whether it's an ideal gas or whether it's a refrigerant or steam. I don't care what it is. If you have, now that's a big if you have an isobaric process, now I was just picking on Parker. Parker, do you remember what delta H is equal to if you have an isobaric process? Parker, go for it. What is it equal to, Parker?
H2 minus H1.
That's correct. Yeah, of course. Yeah, but what is it equal to? What does it give you? Wait a minute. I want to get rid of all these pictures here. Yeah. What does the delta H give you, Parker? Go for it.
I don't know.
That's okay. You're going to learn something, Parker. I showed you this. I showed all of this to you guys. It gives you the heat transfer per mass. And that's important because you like to be, Parker, you like to be cool when you get in your car and go someplace in the summer, don't you, Parker?
I do.
Yeah. Well, that's heat transfer. And it's important to you. You like to be cool. Or in the winter, same thing. You want the heat transfer going the other direction so you can warm up. And guess what? That costs money. It costs money. Heat transfer costs money. You know that. You have to pay for it. You have to pay for it when you run your air conditioner at your house or in your car. It costs money. And so this is important. But now be careful. That only works for isobaric processes. If you don't have an isobaric process, and let's say you wanted the heat transfer, you could use this. As long as I'm talking to Parker, I'll pick on him one more time here. Parker, this is an important equation. What's the name of it? I'll give you a hint. It's the most important equation in the whole course. Parker, what's the name of it?
Not sure.
That's okay. Because I don't learn things the first time around either, Parker. I have to hear stuff over and over and over. Parker, that's the first law of thermodynamics, okay? The most important equation in the course. And look, if you could figure out a way of getting this delta U and this little w, and you took algebra in school, you can get the heat transfer that way. That's another way of getting the heat transfer. Okay, good. That's good. Well, we're going to move on to our next important topic now. And what is that going to be? Let's see. Oh, yeah. Our next important topic is the polytropic process. Now, this is in your book, and I'll tell you where it is, someplace in here, polytropic process. Well, You know, you could read the book. That's another thought there. Yeah. Polytropic process. Well, I can't find it. Yeah, there it is. It's in chapter 3. In my book, it's on page 72. In my book, I'm just curious out there. Is it on page 72 in your book, or do we have somebody look on page 72 in their book and see if it talks about the polytropic process. Do we have the same page numbers?
It's that in my book.
Same page number. Okay, good. Now what this is it's a curve fitting. It's a curve fitting device. You've seen those before on computers. You plot a curve, and then you push a button, and the computer gives you an equation, a function that will fit the curve. Well, that's what this is. And here's the polytropic equation. They call this the polytropic equation. And it goes like this. P, that's pressure. Little v, that's specific volume, to the n power is equal to a constant. In other words, P1 V1 to the n will equal to P2 V2 to the n. If you have a polytropic process, equals a P3 V3 to the n, and etc. and etc. It's they call it a polytropic process. Now, n can be anything. N can be anything from minus infinity to plus infinity. It can be any number, negative or positive whatsoever, and it will fit thousands of different curves. Now, like for instance, if n is equal to 0, then what you have is P1 V1 to the 0 is equal to P2 V2 to the 0. Now you guys all know what V1 to the 0 is. Here, I'll pick on somebody. Here, let's see. I'll find my friend here. Stuart, you helped us out earlier. Stuart, what's V1 to the 0?
1.
Yeah, it's just 1. So what you got here is P1 times 1 equals P2 times 1. Stuart, when P1 is equal to P2, there's a special name for that. Stuart, what do they call that? See, and of course this would keep on going. P3, V3 to the 0, la, la, la. What do they call it, Stuart? When P1 is equal to P2 is equal to P3 is equal to, what do they call that?
Isobaric?
That's it. That's it. It's an isobar. So if n equals 0, you've got yourself an isobar. So polytropic equation will fit isobars. You get an isobar. Now, if n equals to 1, then what you have is P1 V1 to the 1 equals P2 V2 to the 1 equals blah, blah, blah. I tell you one way that can happen is if you had an isotherm, because see, P1 V1 to the 1 is equal to RT1. Well, if the temperature doesn't change, that would equal to P2 V2 to the 1, which would equal to RT2 if the temperature stays the same. And so if N equals to 1 and you had an ideal gas, then you're talking about an isotherm, aren't you? It's an isotherm. So see, the polytropic equation can fit isobars. It'll fit thousands of different processes. Now, let me draw you those on your PV diagram. Let me make some room here. You could read all about this. It's in your book. It's on my book at page 72. Page 72, and you could read about it. But see, if you make a PV diagram, let's say you had air. And say I drew an isotherm on there. Here we go. You know what isotherms look like. They're hyperbolas. Remember me telling you that? Suppose you're at some particular, here's state 1. You're at P1 and you're at V1. Now, if you follow that isotherm and you go up here like this to state 2, then N is equal to 1. It's an isothermal polytropic process with an ideal gas. But now if you went here flat like this to state 2, you're staying on your isobar, and that would be an N equals 0. But by the way, they have a name for this N. It's called the polytropic constant. This value of N is called the polytropic constant. That's its name. Now here's something interesting. If you had a process that went in between, let's say you had a process that went from state 1 to state 2, say state 2 is here. Well, see, N equals 0, you go flat. N equals 1, you follow that hyperbola. I wonder what would be a value for following this process. Well, it might be, I don't know, something in between, like maybe 0.5. Does that make sense? If N is 0 when you go here, and N is 1 when you go there, then something in between might be 0.5 or 0.4 or 0.6 or something like that. Now, let me ask you a tough question. Suppose you come up here like this, and you go from state 1 to state 2, but you're on that side of the hyperbola. Let me ask somebody. Let me find somebody here. Megan, I'm going to pick on Megan. Megan, what would be a value for the polytropic constant if you went from state 1 to state 2 here? Megan, want to take a guess?
It'd be something over 1.
Yes. Yes. I don't know. It could be all kinds of things. It could be N equals 1.75, or it could be N equals 2 or 3 or 4, whatever. It's going to be something bigger than 1. Now, I got another one here. I'll pick on somebody else. What if you had a process that came down here to state 2? Now, let me find my friend Cameron. Cameron,
Yes.
What if you went from state 1 to state 2 down here? What would be a value for n? Now remember, n is 0 here, 0.5 here, 1 here, maybe 1.5 here. What would be, Cameron, what would be a value for your polytropic constant going from 1 to 2 down here? Go for it, Cameron. He's thinking.
What was the one right above that?
This one, Cameron, this one right here was
Yeah.
n equals 0.
So would it be -1?
Yeah, good going. It'll be negative something. Now it might be negative, I don't know. There's a million different things it could be. It could be negative, I don't know, 1.5 or negative 0.8 or negative 0.75 or negative 3. You understand there's a million things it could be, but it'll be negative. Cameron's got that figured out. Okay, good. All right, now I'm going to show you how to find the work. Now we're going to find the work per mass in a polytropic equation. I'm going to erase all this stuff, and then we're going to find the work per mass. But before we do, was there any other comments or questions? I shouldn't have erased that. You might need that. Nobody has any comments or questions. Okay, well, here we go. We're going to find the work. Now, this is in your book. It's on page 73, maybe. Page 72, 73. It's right there in your book. You could read it. Anybody have a comment or question? Yeah, well, okay. Right now, we've talked to you about something called a polytropic process. And if I ask you, well, what the heck is a polytropic process? The answer that I would want you to give me is it's a process that obeys the polytropic equation, which you could just write it like this. There you go. It has to obey that equation. Then it's a polytropic process. Okay, well now if you want little w, remember that's the integral of p dv. And what we're going to do is we're going to do some calculus here. You'll love this. P is equal to k over P is equal to k over little v to the n. I bet you can get from here to here. I'm confident you can. Okay, well then you could write this as k over little v to the n dv. Couldn't you, calculus students? I hope so. All right, and of course, you'd have to go from V1 to V2 to integrate this thing. Now, we all took calculus, so we can do that. By the way, this constant would be P1 V1 to the n, or P2 V2 to the n, or P3 V3 to the n. They're all the same. But when you integrate this, yeah, let's don't skip any steps. Let's write it like this. Can you get to here? Calculus students, can you get to there? I hope so. All right. Well, when I integrate that, what I get is this here. I get the work per mass is equal to V to the minus n plus 1 divided by minus n plus 1. Don't forget to multiply by K. Now you have to put in these limits from V1 to V2. Okay, well, let's see what we get here. Now K, keep in mind K is equal to P1 of V1 to the n. It's also equal to P2 V2 to the n. It's also equal to P3 V3 to the n. So what I'm going to do is I'm going to write P2 V2 to the n, that's equal to K, times V to the minus n plus 1 minus, and then I'm going to write K as P1 V1 to the n times V to the minus n plus 1. I need to put a 2 there and a 1 there. Those are all divided by minus n plus 1. Can you get from here to here, calculus students? I bet you can. Or algebra. All you need is algebra to do that, really. Okay, well, we're almost through now. See that V2 to the n and the V2 to the minus n? They go bye-bye. And what you're left with is little w is P2 V2 minus P1 V1. See, the n and the minus n, they go bye-bye. Divided by, we'll write this as 1 minus n. By Jove, we've got it. That's the equation. Now, see if you can find that equation. I don't see it. I'm looking. There it is. It's got numbers in it. Yeah, there it is. I see this equation on page 72, but they wrote it with big letters. Well, that's okay. You can write it with big letters. Here, let me write it with big letters up here. We are studying the polytropic process. It's a process that follows this equation right here. And we have just calculated the work per mass. The work per mass is P2V2 minus P1V1 all over 1 minus n. We have come up with a wonderful equation. Now, the book comes up with the same equation, but they write it as big W. And what they have is P2 big V2 minus P1 big V1 all over 1 minus n. It's the same equation. It's just written with big letters and little letters, and I hope you know the difference by now. The difference is big W is equal to little w divided by the mass. So we have a lovely equation. Now there's a little glitch, a little fly in the ointment on this equation. You can't have n equal to 1, because then you'd have a 1 minus 1 in the denominator. And the mathematicians don't like that. They go into a, I don't know, kind of a hissy fit. They don't want any zeros in denominators. So yet we've talked about when n equals 1, and so we have to come up with a different equation for when n is equal to 1. Now we've already done this for an ideal gas, But this equation we're going to do now works for whether you have an ideal gas or not. Okay, well, let's do that if you're happy with that. We have just come up with an important equation for the work done with a polytropic process. And remember, the polytropic process fits 1,000 different processes. It's kind of a curve fitting thing. Any comments or questions so far? Well, now you guys follow the schedule. I think there's some homework. I'm not going to tell you when it's due because the last time I did, I told you the wrong date and I had to extend it. But it says right on there, if you'll click on your Blackboard, it tells you what your homework is and when it's due, and turn it in on time and I'll grade it. If you turn it in before the due date, I'll grade it. Okay, well, let's show you what happens when n is equal to 1. I just need, we'll keep that here maybe because that's an important one. But let's do it when n is equal to 1. Here we go. If you didn't understand that, you could read about it. It's in your book. It's on page 72. It's right there. I see it. Now what if n is equal to 1? What if you have a polytropic process and n is equal to 1? Well, then PV to the 1 is equal to a constant. And the work per mass is equal to P dV. Yeah. But see, you could write P as K over V. And so you could write this as the integral of K over V dV. Now you guys all took calculus and you know what that integral is. It's K, the integral of dV over V. Now in calculus, you've done this. The integral of dx over x, do you remember? You remember that's equal to the natural log of x, isn't it? Well, they just did theirs with x's. We're doing ours with v's. So it's the same thing. It's going to be k natural log of v. Now we're going to go from v1 to v2. Keep in mind that k is equal to p1 v1 to the 1, which is equal to p2 v2 to the 1, which is equal to p3 v3 to the 1, which is equal to p4 v4 to the 1, dot, 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 forever. And so, little w, the work per mass, is equal to k, which you could write as p1 v1, natural log of v2 over v1. We have just come up with the formula, and that also is on page 72. I see it at the bottom on my page 72, only again, they did it in big letters. In my book on page 72, they've got big W is equal to P1 big V1, natural log of big V2 over big V1. But it's the same thing, because you guys know to get from one to the other, all you got to do is divide that by the mass. and you'll have the other value. We have just come up with some wonderful equations for polytropic processes, and now we're going to work some problems. But are there any questions? Are there any questions or comments? Well, I guess not. Let's see if everybody's still on board. Yeah, we've got a pretty good crowd here. Pretty good crowd. Let me take roll here and just see who's here today. Today's the 15th. I'll take roll here. We've got Stuart, Spencer, Parker, Megan, Cameron, and Bear. Okay. Well, I don't guess you have any questions. So we're going to work a problem now. We've got two lovely equations. And I thought we could work problem 3105. Let me make some room here. We'll work problem 3105. You guys didn't have any comments or questions. Okay, now let me find this 3105. Okay, now this is air. It's air. And it goes polytropic process, N equals 1.3. It starts at 2200 kilopascals. Let me write that down. 2200 kilopascals, 1800 Kelvin, and ends with a pressure of 200 kilopascals. They want to know several things. One of them is the work per mass, and we'll get that. And then they want the heat transfer. We'll get that. Okay, now there's a secret to doing problems in this class. If you want to be successful in this class, you got to know this secret. The secret is the PV diagram. You've got to put the process on the PV diagram. I wonder if I could get rid of those. Well, I like seeing you though. That's kind of nice. It takes up part of my space, but that's all right. Okay. Well, let me get my 1800K in there. We know that 1800K is going to be a hyperbola. It's kind of shaped like that. 1800K. Everything on that line is 1800K. All right. Now we're going to go from 22. Here's state one. It's at 22 100 kilopascals, and it's going to go down here to 200 kilopascals. Now, if n was 1, then you just follow down this isotherm. Remember, we talked about that. And state 2 would be right there, wouldn't it? See, if n was 1, if n was 1, you just follow down that isotherm and you'd be at state 2. But you know what? N is not 1. N is 1.3. Now remember, if you went over this way, that would be n equals 0, wouldn't it? See, n equal 1 goes down this way. N equals 0 goes flat, remember? Isobars are n equals 0. But we got n equals 1.3. Well, where the heck is that? Well, it's not in between here. You see, something in between here would be like n equals, I don't know, 0.5. Y'all, little Southern talk, y'all understand that? If you came in here in between here, a value could be n equals 0.5. We don't have 0.5. We don't have 0. We don't have 1. We have 1.3. Well, where is that? Well, it's down here. Can you guys see that state 2, n equals 1.3 is like that. You don't go down the isotherm. You don't do the isobar. You don't go in between. You come down here. We're showing you how to do a process on a PV diagram. Okay, well, great. So what? Wait a minute. They said it's an what's the word? Polytropic. So we have an equation that goes like this. P1 V1 to 1.3 equals P2 V2 to 1.3. Now let's circle the stuff we know. Well, we know P1. We don't know V1. Too bad. We know P2. We don't know V2. Hey, but wait a minute. This is an ideal gas. It's air. So looky here. P1 V1 is equal to RT1. We know P1. We know R. We know T1. Hey, we could get V1. Do you see it? We could get V1. Now, I'm going to shut up for a minute and a half. And I want you to do it. I want you to participate in this class. I want you to get V1 for me. We know P1. You know R for air, or you could look it up. You know T1. I'm going to shut up. Find V1. You got a minute and a half, go. And then I'm going to ask somebody. So do it. It'd be good for you. Go for it. Wonder how I'm doing on battery. I can't tell. Maybe I should plug this thing in. Okay, I did that. And I'm going to pick on somebody and see what they got. I got an answer. But let's see about some of you guys. Aubrey. I haven't picked on you all day, Aubrey. Did you get this specific volume at state one for me?
I got 0.2348 meters cubed per kilogram.
That's exactly what I got. It's so easy to teach this class with these wonderful students. Makes it easy. Okay, now looky here now. I've got this thing with all your names on it. Does that show up on your screen or not? I'm going to get rid of it because it's in my way. There. Now I just have the PV graph there. Okay, now look at here. We know V1 now. Now we have an equation. We know everything except V2. We're going to solve for V2. See, here's V1. V1 is 0.2348. Aubrey and I both got that same answer, 0.2348. And now we're going to get V2. You've got the equation, you know everything in it except V2. I'm going to shut up again for a minute and a half. And I want you to get V2. Okay, on your mark, get set, go. See if you can do it. Well, I got an answer. I'm not sure that it's right. Bear, I haven't picked on you all day. Bear, do you have that V2 yet?
I do not.
Take your time. Take your time. How about Stuart? Stuart, do you have that V2 yet?
Yes, I got 1.4853.
That's what I got. Now, does anybody need me to write that out carefully? Because I'll be glad to. I think that's your V2, 1.485. But you're going to have to ask me, otherwise I'm going to go on. Anybody need that written out that had trouble with that? If you had trouble with that, we'll write it out. If nobody asks me, we're going to go on and calculate. We're going to calculate the work done. All right. Did anybody need help with that? Well, I guess not. I guess you got it okay. I hope so. All right. Now we're going to find the work per mass. Now remember, the work per mass, that little W that we're trying to get now, it's the area underneath that graph. See, this is our process. Do you understand? This is our process. We did not follow the isotherm. We followed a different process. It's a polytropic process, n equals 1.3. Okay, we're going to find little w, and remember, here's how it goes. P2V2 minus P1V1 all over 1 minus n. Now what is P2? That's the 200. Here, I'll write it out for you this time. And V2 is the 1.485. P1 is 2200. And V1 is the 0.2348. And then you have to divide by 1 minus 1.3. Okay, I'm going to do that. I'm going to find out the work done. Here goes. Well, I got an answer. I got 731.9. I wonder if that's right. I did this before. Let me look it up and see if that's what I got before.
That's what I got.
Yay, I bet it's right. I bet it's right. Okay, now the work came out positive. I told you about there's positive work and there's negative work. And I told you about it. Does anyone remember what happens when you have positive work? What happens when you have negative work? You remember? Positive work is when you do something. Well, what is that something when you do positive work? Here, let me go to my friend. We'll go to Aubrey. Aubrey, what is it when you do positive work?
You expand?
That's it. That's it. Well, look here. We're expanding. We're expanding, aren't we? Now, I didn't do a device sketch. I think we should. We'll do it. There's some room right here. Let me draw a device sketch. Here we go. There's a little bit of room right here. This could be state 1. And this could be state 2. Now, state 1 is down here, and it's got a heavy weight on it. State 2, they took the weight off, and it expanded. That kind of makes sense. If you take that weight off, the volume will go up. Hey, look, the volume went up, didn't it? Yeah, the volume went up. It expanded. You did positive work. But what was the heat transfer? Well, usually when you expand like that, usually it gets cooler. So usually the heat transfer is out, it's negative. But I don't know, we'll find out. We found out the work per mass. Now they call that the specific work. But we haven't found out the heat transfer per mass. I need a little room to operate here. We'll sacrifice some of this stuff. Now, here's what you have to do. You have to go delta U equals Q minus little w. We've got little w. It's 731.9. We got that. If we could only get delta little u there, we could solve for the heat transfer. Anybody know how to get that delta little u there? I'll wait and see if anybody knows. We showed you the other day. Do you remember how to do that? Well, nobody's going to speak up, so I'll start with my friend Stuart again. Stuart, I'm always picking on you. Stuart, do you remember how to calculate this delta U thing?
Not off the top of my head.
Well, that's why you're taking this class, see? You're gonna know here in just a minute. Well, one way is you do this, Stuart. You go C sub V delta T. And we'll look up C sub V. In the back, you can look that up. We'll just use the unhappy face value. It's, I think, 0.717. I'm not sure about that. Yeah, that's right. Kilojoules per kilogram Kelvin. And then we'll take T2 minus T1. T1's 1800. But here's my problem. I don't know what T2 is. See, there's going to be a T2 through here. I'll draw it for you. Here it is. Oh, there's a T2, all right. Kind of messy there, but you got the picture. There's your T2. See, this T1 here is the 1800K. If we could only figure out that T2, We know this CV, you could look it up, make sure I did that right. And you could get delta U. And see, once we got the delta U, we could find the heat transfer. Okay. But we need that T2. How are we going to get T2? How are we going to get T2? Anybody know?
The ideal gas equation using
That-
that volume.
That's it. You got it. Exactly. So what we're going to do is we're going to go P2 V2 equals RT2. Well, what's P2? That's the 200. P2 is 200 kilopascals. And V2, oh, that's right, sitting right there. That's the 1.485. And then the R. Oh, looky here, we can get T2. Go ahead and get that T2. All right, I'm going to do it. You do it. Well, I got a T2. I'm getting a T2 equals to 1034.8 Kelvin. It's a little cooler, isn't it? It started off at 1800 K and it cooled off to 1034.8 K. And so now we know T2, looky here. So we can solve this and get delta U. So here goes, I'm going to do it now. Well, I wonder if I did that right. I'm getting a delta U of negative 548.6. Anybody getting what I'm getting? I need an
Yeah, I got that. And
Yay.
it's negative because our T2 is less than our T1.
Very good. What was that, Aubrey?
It was Megan.
Hi, Megan. Good going. I'll learn your voices someday. Okay, now look at here. We know Q. Now there's a negative in the equation, and the work is positive. It's 731.9. So we can get the heat transfer. Go for it. We're going to get the heat transfer now. I'm plugging that in. I got an answer. I got an answer for the heat transfer. I got a positive, well, it's heat transfer per mass. 183.3 kilojoules per kilogram. Now I want to make sure that's what I got when I did this before. This was problem 3105. We'll see what I got before. 3105. They got a Q 183.4. That's what I got. Yeah. 183.3, 183.4. I'm happy with that. Well, what does that mean? Positive. You know what that means? That means that there was a heat transfer. It's positive. That's going into. It's going into. Now we have two contradictory processes here. We're taking a weight off. That should cool it down, and it does. It cools down. See, it cools down to 1034.8 K, where it was what, 1800 K. But we have a heat transfer in that would tend to make it warmer, wouldn't it? Well, here's the deal. You got two opposite effects, but the boss, the big effect is when you take that weight off, it has a bigger influence than this heat transfer. By the way, the book calls this specific heat transfer. Well, we did that problem, and I hope you're happy with it.
I have a question.
Yeah,
If Q is negative 548.6 and we're subtracting W, which is a positive 731.9,
yeah.
why is
uh-huh.
the answer 183 instead of negative 1280?
Well, we think Q is 183, right? Didn't we? Did you just say
Oh,
Q?
I wrote Q delta U as Q and vice versa. I
No.
flipped them.
You're okay now?
Yeah.
Yeah. See, Q is 183. Now, the book calls this specific heat transfer, which is fine with me, but don't get them confused. I need a little room to write here. We did that problem correctly. I wish I could find some room. How about down here? I'm pretty happy with all this stuff down here. Little q is called specific heat, being lazy there, transfer. Specific heat transfer. C sub V is called specific heat. Notice it doesn't say transfer after it. See, specific heat transfer is one thing. Specific heat is totally different. See, the units on specific heat transfer are kilojoules per kilogram Kelvin, and the units on specific heat transfer, did I say it wrong? That's kilojoules per kilogram. See, there's a difference between kilojoules per kilogram Kelvin and kilojoules per kilogram. It's a big difference. It's kind of like the difference between miles and miles per hour. How fast are you going? 60 miles per hour. How far did you go? 60 miles. You don't get them mixed up. You don't say, how fast are you going? Well, I'm going 60 miles. That's not how fast you're going. These are totally different concepts. This is called specific heat transfer. And this is called specific heat. I hope you're not too confused. Okay, what we're going to do is I'd like to show you a little shortcut. In order to find T2, we use the ideal gas law. Well, first we had to find V2. And then once we got V2, there's V2. Then we used the ideal gas law, P2, V2, and we found T2. I want to show you a shortcut when we come back in after a 10-minute break. And I want to show you a lovely shortcut that you can use with ideal gas polytropic processes. But I think it's time for a 10-minute break. What about you guys? Unless you strenuously object, we're going to take a 10-minute break. Does anyone strenuously object? How about you, Parker? Do you strenuously object?
No.
Okay, well, Parker says go ahead and take a 10-minute break. We'll be back. We'll be back in 10 minutes for more fun. Go stretch. And I'll show you some more And we'll have some more fun here in just a little bit. Well, I wonder if I've still got a class here, or if everybody left me forever. Let me see. Oh no, we've still got some diligent students that haven't deserted me. Yeah, good. Okay. Well, I saved a little info from our problem. We did problem 3105. Oh gee, I didn't write down the work. Here, let me write that down. We did problem 3105. And the work was little w was 731.9. And hopefully you understood all that. Now I want to show you kind of a shortcut equation here that I really like. You just have to be careful with it, that's all. The equation that we're going to talk about is this one here. Now this equation you got to be careful with. Now I've got a picture of me that's interfering with you seeing this equation. I don't know how to move that picture of me. Maybe there's a way to get rid of it. Show small active speaker video. Hide. There we go. I got rid of it. Yeah. Now it says talking. Vince Griffin. I don't want it to say that. I hope you can read that. Talking. Oh, that moves around. I can maybe get rid of that. Yeah, but I want to be talking. Maybe I should leave it alone. Okay.
I can see the board just fine.
Good. Thank you. Okay. This is a shortcut equation, but you got to be careful with it. It only works for a polytropic process. See that little n there? That little n is called the polytropic constant. It's the polytropic constant. So if you have an equation with that little n in it, it darn well better be a polytropic process or you can't use it. It's a nice equation, and let me show you where it comes from, okay? Here we go. We're going to show you that. Now, it comes from P2V2 is equal to RT2, and P1V1 is equal to RT1. Oh, here's something else, too. This only works if you have an ideal gas. If you don't have an ideal gas, you may not use this equation. So I'm going to put a skull and crossbones on this equation. In other words, don't use it unless you have an ideal gas and you have a polytropic process. But we do. On problem 3.105, we did have an ideal gas. We had air and we had a polytropic constant. But we're going to show you where this equation comes from. Now, if you divide these equations, they're equals. Did you know if you divide equals by equals, it's mathematically okay. So if you do that, you can get T2 over T1. The R's cancel, and you'll have P2V2 all over P1V1. Can you get from here to here? Okay, now see, if you have a polytropic constant, then the P1V1 to the n is equal to P2V2 to the n, if it's a polytropic constant. And so come down here, P2 over P1 should equal V. No. I'll get this right in a minute. V2 over V1 to the n is equal to P1 over P2. Can you get from here to here? I think that's legal. Okay. And what we're going to do is I want to get rid of those V2s. Now see if you can do this. V2 over V1 is equal to P1 over P2 to the 1 over n. I went from here to here. It's an algebra trick. I think it's good. So now I can substitute that in here. And what you'll get is P2, P1 to the 1 over n divided by P1, P2 to the 1 over n. Or you could just go like that. There we go. Yeah. Okay. We're doing algebra here. If you don't follow this, you could probably do it on your own at home. But this is how you get it. Okay, now I'm going to set that equal to something. Need the room here. That should equal P2 over P1 times P2 over P1 to the minus 1 over n. I did a little algebra trick there. I hope that you can follow me. And see, you can put a little 1 up here in the corner. And so what you have here is P2 to the 1 minus 1 over n all over P1 to the 1 minus 1 over n. That's equal to that. And you could write this as P2 over P1 to the n over n, the n minus 1 over n. There we go. Hey, we just came up with this equation here. We started we started with T2 over T1. We did a bunch of steps here. You might have gotten lost, but you could do this at home, and this is what you come up with. Now, I could take up more of your valuable time with the algebra, but this is not an algebra class. I bet you could get to here. You use the same stuff that I did to get to there. I'm not going to bore you with that. The bottom line is you've got this equation. As long as you've got it and you know when to use it, it's got skull and crossbones. It's only good for two things. One of them, it's got to be a and the other one, it's got to be a something. If you don't have those two things, do not use that equation. Well, what are the two things? Well, here they are. You've got to have an ideal gas. You've got to have a polytropic process. Otherwise, do not use that equation. All right, now let's plug it in and see if we get the same answers. We did not use that equation to get these answers. But let's do it and so that you'll be convinced that it works. Okay, here it goes. Well, T2, we're going to solve for it. We solved for it another way. We found the specific volumes with the ideal gas law, and then we plugged in, we found the specific volumes with the polytropic condition. Then we plugged in the ideal gas law. That's how we did it. Now T1 is 1800 Kelvin. P2 is given. P1 is given. N is given. So here's our equation. Now we're going to solve that for T2. And if we're really lucky, we're going to get the same answer we got doing it a different way. Here goes. Okay, I'm doing all that now. Okay, here's what I'm getting for T2 when I plug in this equation. Now what did we get doing it there? Oh, it came out, I'm off a little bit. I must have rounded off something someplace. I like this answer a lot. It's right on the money. You know what? When we did our specific volumes, we probably rounded off something. But see, it works great, doesn't it? You've got your, well, let's see if this works here with the specific volumes. Let's see if that works. Now, what is the V1? 0.2348. Now, notice this is 2 over 1, 2 over 1, but this is 1 over 2. Watch out for that. Okay, there's V1. Now, V2 is 1.485 to the 1.3 minus 1. Okay, well, let's see what happens. I'm plugging this stuff in now. Now, when I plug this in, I'm getting 0.5750. Now I'm going to plug this in and see what I get. Hopefully, it'll be 0.5750. I'm hoping. I didn't get that. Let me try it again. Must have done something wrong. Did I get V1? And V2, yeah. Yeah, it worked out beautifully. I'm getting 0.5750. In other words, this whole equation works great. It worked great. Write that down, but watch out. Don't use it unless you have the right conditions. Okay, now what's next? What is next? I want to do an English problem. This is 3-176E. Does anyone have a question on any of this? Because we're going to erase it if you don't. Okay, well, if you're happy, I'm happy. We'll say goodbye to all that. Okay, now we're going to work a problem. And this one is 3-176E. Now we're dealing with R134E. I mean R134A, right? R134A. That's what you have in your car air conditioner. I got to find this now. What does that E stand for? 3-176E.
English units.
It's English units. We've got to learn how to work in English units. Now, if the problem is in English units, you stay in English units. You work the entire problem in English units. You don't use the metric or the SI. Now, if the problem is in metric or SI, you work the problem in metric or SI. You don't use English. You got to learn how to work entirely in either system. Okay, well, let me see what this is. Cylinder, I'm reading this, a frictionless piston, 4 pounds mass. Okay, let me write that down. You got 4 pounds mass, superheated R134A. Superheated vapor is what we're talking about. You know where that is. At 400 psi, let me write that down. 400 psi and 200 Fahrenheit. Okay. The cylinder is now cooled, so the R134A remains at constant pressure. We have an isobar, constant pressure, until it reaches a quality of 25%. They want the heat transfer. Okay, great. We're going to go all the way to a quality at state 2 of 25%. All right. Now there's a secret to success in this class. It's this thing here. Until you get the hang of these, you're going to have trouble. You've got to get the hang of these PV diagrams with a process on it. Okay, now this is a refrigerant, so it's got a vapor dome, what I call a vapor dome. It kind of goes like that. Maybe not. There we go. There we go. Now, these vapor domes are a little bit like the Sierra Nevada mountains. Well, on the western slope, it's real gradual. The elevation slowly increases until you reach the top there. The tippy top is Mount Whitney. It's 14,000 feet. But then it's just a real steep drop off to the Owens Valley. The PV vapor dome kind of looks like the Sierra Nevada mountains in California, sort of like that. Now we're in superheated vapor at 400 psi, 200 Fahrenheit. So get out your R134A and start thumbing through there on your computer or cell phone. It's in Fahrenheit, so we need English stuff. And I want 400 psi. Hey, I found it. I found it. I'm on table F7, F.7.2 is where I'm at. And they have 400 psi, and we need 200 Fahrenheit. Well, I can't find it. Let me read this again.
Shouldn't we be using a different table? Because
Yeah, I'm on the wrong table. Just a minute.
I think it's F10.2.
Yeah, this is wrong. I'm going to give you a honking. Who was that?
Spencer.
Spencer. I was on the wrong table, Spencer. But I'm on the right table now. Okay. Got to be on the right table. Hey, I found it. There it is. 400 psi, 200 Fahrenheit. Why don't I write down some stuff? Here goes. Little v1 is, well, this is table F.10.2. Here, let me write that down. F.10.2. And Spencer got a thank you point because I was on the wrong table. But I'm on the right table now. And this is 0.1146. And this is, I'm writing this stuff down. This is 184.44. You're supposed to put the units. So I'm going to put the units on there. Hope you can read my writing. That's a little h1, and it is 192.92. Okay, we wrote down some stuff. Now let's put our isobar in there. We have a 200 Fahrenheit isotherm. 200. You know what? It's pretty up close to the top of that vapor dome. If you go to table F.10.1, F.10.1, if you go to that table, you'll see that the 200 Fahrenheit isotherm, dang close to the top. It goes like that. Now that's the 200 degree Fahrenheit isotherm. Everything on that red line is 200 degrees Fahrenheit. That's what it looks like. And see that pressure right there on table F.10.1 is 589 something, 589 something PSI. But we're at just 400 PSI. We're down here someplace, guys. 400 PSI. So that means we are located, there's our state 1. All right. Then what? Let me keep reading this.
Isn't our pressure for 200 degrees Fahrenheit supposed to be like 503 from the table?
Did I read the wrong thing? 200 degrees Fahrenheit. Yes, this is wrong. I don't know what I did. Who knows what I did? If you're at 200 degrees Fahrenheit, that pressure is 503. Now, who was that person that just told me that? Was that Megan?
Yeah.
Megan, honkin' thank you point for Megan. Good going. I don't know what I did to get that other number. Beats the heck out of me. I don't know what I did, but Megan's right. But see, we're at 400 and there's state 1. I think everything else is right. Now you guys jump on me now if it's not right. See, Megan helped us. And if I don't have anything right, you yell, let me know. Okay, now let's go back to our problem. And we're doing 3/176E. I think I've got everything right so far. Now we're going to cool it at constant pressure till it reaches a quality of 25%. Well, here we go. We're going to go constant pressure. We're going to go constant pressure to state 2. We're going to be out here in superheated vapor, and then we're going to go to state 2. Now let's get all the information at state 2, shall we? Here we go. If you wanted V2, you have to go VF plus the quality of 2 times VFG. I talked to you about that equation recently. And let me find that. Okay, trying to find it here. Okay, I'm kind of getting lost here. Oh, I'm not. I'm not lost. I can find that VF at 200 Fahrenheit. No, wait a minute. No. We need 400 PSI. Well, I tell you what, guys, they don't have exactly a 400. They have awfully close. You see that 400.392? I'm not going to interpolate. I'm just going to go with that one. And so this is going to equal 0.01760 plus 0.25, 0.0787. That's how we're going to get little v2. Now let's get little u2. Now little u2, it's the same doggone thing. It's the uf plus x2 ufg. And at state 2, we have 400 psi. They don't have a 400 exactly, but I am not going to interpolate that. It would be nasty. Being lazy, I am going to use 139.32 plus 0.25 times 3791. And let's get H2, little h2. Here we go. It's the same boring thing. It's, oh, you have to flip the page though to find it. In my book, I'm finding it here. I need, and where are we at again? We're at 400 psi. They don't have a 400, but we're going to use 400.392. That's close enough for me. And I'm getting 140.62 plus times 4374. Now I'm going to find those in a minute, but I want to make sure that you all, every one of you, can find those numbers in your tables. So I'm going to shut up for 60 seconds and go back to the tables. We're talking R134A tables. They don't have a 400 exactly. They have a 400 point something, but it's dang close. And see if you can find those numbers. Can you?
I can.
That's what I like to hear. Now who was that?
That was Stuart.
Stuart, good going, Stuart. I won't pick on you anymore since you helped me there. I'll pick on somebody else. You guys really don't mind me picking on you. It's character building, isn't it? Okay. Well, good. Let me go ahead and calculate all of these. And then we'll do our problem. We'll solve it. Here goes. A lot of this course is just tedium and boring, and it's not hard. It just punching buttons is what it amounts to. But isn't that what they do at the bank with your money? Of course, they have computers to do it. They have computers to do this too. Okay, here's what I'm coming up with. And I hope somebody is double checking me there. And now, if those are correct, we're going to find what they wanted. If you just woke up from a daydream, we're doing problem 3-176E, English. English, senor. Now we're supposed to calculate the heat transfer. Okay, well, there's a couple of ways to do it. The easiest way since this is a isobaric process, see, it's isobaric. They said it was. They said it was an isobaric process, didn't they? Constant pressure. Yeah. What do you know about an isobaric process? You know that the heat transfer is the change in your specific enthalpy. Well, that's easy. Look at here. We've got H2 and H1. There's H2 right there. There's H1 right there. And we're going to get the heat transfer. Go for it. Plug it in. Boy, that was easy. Well, I got an answer. I'm getting negative 41.36 BTUs per pound mass. That's not what they wanted. What they wanted was big Q. Well, big Q is equal to M times little q. If you have 4 pound mass, just multiply that by 4, and you'll
I
get,
think our enthalpy should be, you have them backwards. You have H1 minus H2 when it should be H2 minus H1.
oh,
And then you should get a positive 41.36.
okay. Now, is that Megan?
Yeah.
Megan, I think you got a thank you point already, didn't you?
Yeah.
Good for you. There's no law against getting 2 of them. I did something wrong. Now let me see if I can do it right. I don't think this is right. I think Megan's right. I want to take H2, which is 151. See, without you guys, I can't do this. And then I'm going to subtract H1, which is,
Oh, wait. I think I'm wrong, actually.
oh, well,
You were right.
I'm going to have to erase that thank you point, Megan.
That's okay.
It's not the end of the world. I'm still getting negative 40. Is that what I got before? We're going to have to
Yeah.
erase. We'll erase.
I had my enthalpies backward.
But that's how you get these thank you points. Now, students have asked me, well, what good are the thank you points? Well, I haven't figured that out yet. What you should get, if you have enough thank you points, you should get a cherry red Corvette. Well, that would be a pretty good reward, wouldn't it? A Corvette convertible. A cherry red Corvette convertible. Would that be a pretty good prize for getting the most thank you points? Trouble is, I can't afford it. But anyway, that's what you should get. Okay, well, now we figured out the heat transfer. It's negative. That's interesting. But if you'll think about it, see, when you go this other way, when you go to the right, see, going to the right is boiling. And if you want to boil something, don't you have to put heat transfer in? Don't you have to turn on, like on your boiling water, don't you have to turn the stove on? And either you have electric or gas stove, and you heat up the water and you get it hot and it boils, and you go from here to you go to the right. That's boiling. And when you do boiling, the Q is positive. That almost makes sense. But see, we're not boiling here. We're condensing. They call that condensing. And when you do that, the Q is negative. It's less than 0. It's negative. We need to draw the device sketches and show you that. But first, I wanted to show you the other way. Now, the other way of getting this heat transfer, I think we did it right. Oh, did we ever get this? I need to multiply that by 4. I'm getting negative 165 BTUs. I wonder, let me check and see if that's what I got when I worked this problem before. This is 3176. 3176. Yep, that's what I got before. I think we did that correctly. But I want to show you another way to get it. Need a little room to do that. There's a little room right here. And here's what we're going to do. Delta U is equal to Q minus W. Now delta U, for this problem here, you can't go C sub V delta T. You're not permitted to do that. Now let me pick on somebody here. And let's see. Spencer, you're not permitted to get C sub V delta T to get that delta U. Why? Why is that taboo, Spencer? It's taboo.
Oh, it has to be an ideal gas.
That's it. That's it. This is not an ideal gas. This is a refrigerant. And in fact, when you get to state 2, that's mostly liquid. You know it? If it's 25% vapor, then it's 75% liquid. So you don't use the ideal gas law on things that are liquids. Don't use the ideal gas law on these refrigerants. That's what tables are for. Use the tables. Okay. So don't use that. I tell you what you can use. You can go U2 minus U1. Now here's U2. And I'm going to take U2. Let me write it down. 148.8 minus U1. Now where's U1? There it is. 184.44 equals Q minus W. Now the W, we don't have the W, but I tell you what it is, guys. It's this area of this rectangle. See this rectangle? We can get it. I need a little room here someplace. I'll sacrifice some room here. Little w is equal to the area of that rectangle, which is the height, which is 400 pounds force per square inch, times the width. Now the width would be V2 minus V1. Oh, gee, did I just erase my V2? I think I did. Dang. Anybody know what the
V2 is 0.037275.
I erased it. That was real smart. I need this room here. But then you'd have to subtract V1 to get this width here. Now V1, I think I still have someplace. Oh, gee. There it is. It's 0.1146. Hey, I think we can get our little W, guys. Here goes. Oh, now wait a minute. Auga. You know what? These are cubic feet per pound mass, aren't they? We're going to have to doctor this up. We're going to have to do this. There's 144 square inches in a square foot. Now we have foot-pounds per pound mass. But we're still not through doctoring it up. To get BTUs, you're going to have to go, a BTU is 778. Oh, gee, I can never remember this. I think it's 17 foot-pounds. Is that right? Let me look that up. I'm going to look that up. Here goes. Looking up how many BTUs, foot-pounds. Yeah, I got that right. Even a blind squirrel finds a nut now and then. And so here we go. We're going to get our little w. It's coming. Here goes. I'm getting, wonder if I did that right. I'm getting 0.0212. That doesn't sound right. Let me try it again. I did something wrong. Yeah, I keep getting different answers every time I do this. Let me try one more time. I'm trying to get the little w. It's the area of this rectangle. We know the height and we know the width, but you have to do this to get the units right. Okay, I'm getting minus 5.7, I don't know, 4 BTUs per pound mass. After about my third try, I'm getting the little w. Here it is. Back to this equation here now. We know what the delta U is. And now we know what the W is. But now wait a minute. Oh, it's a negative. So you got a negative, you have a subtracting a negative 5.72. Ran out of room there. Put a 4 right there. Put my parentheses over here. Okay, now we're going to get Q. Here goes. Now, if we're really lucky, we should get the same answer for Q that we got before. See, before we got negative 41. Well, let's see what we get. Here goes. Let's see, 148.8 minus 184.44 minus 5.724. Well, I'm getting 41, a negative 41.36 something. Well, Shazam, you know what? That's what we got the other way. We got negative 41.36 using the change in specific enthalpy. That was a whole lot easier, wasn't it? Oh, yes, it was, Mr. Griffin. Well, it was. It was a heck of a lot easier. This was sort of a pain. But you know what? We got the same answer. Do we have any questions on 3176E? Well, we don't have much time left, so let me spend our last few moments talking about what we're going to do Wednesday. But I'll entertain any comments or questions from you. I'm listening. Anyone have a comment or question?
I sent you a couple of emails last week,
Yeah,
but I never got a response. I just wanted to make sure I was sending those to the right email address.
okay. Now, is this Spencer?
It is.
It's Spencer. Well, let me check on that, Spencer. Let me scribble down. Spencer sent me emails. Now, my email address is vince.griffin@tulsacc.edu. Is that where you sent it?
Let me double check. I'm logging into my TCC Outlook now. Yeah, that's when I sent it to.
Well, I'll look. Sometimes it gets put in the spam, or I mean the junk or whatever, but I'll look, Spencer, and then I'll email you back. Anybody else
Okay.
comment or question? Well, let me tell you what we're going to study Wednesday. If you guys are happy with all that, that was fun, wasn't it? And you know what the dirty little secret is for success in this class? It's this, isn't it? It's the PV diagram with a process on it. See, that's the process. From 1 to 2. I need a 1, I need a 2, I need a process line going from 1 to 2. Sometimes it's curved. This time it was straight. Okay, now our last few minutes together, I want to talk to you about where we're headed Wednesday. And you have homework. Just go to Blackboard, do your homework, turn it in before the deadline, and I'll put some points in the grade book. Now, chapter 4, everything we've done so far has been with control mass. And the first law simplified is like that. Actually, the first law is really like that. And it simplifies to this if you can neglect your kinetic and potential terms, but you can't always do that. Now this stands for control volume. And see, this control mass, we were dealing with, hey, we never did our, doggone it, I forgot to do my, device sketches on that last problem. Hey, we got 5 minutes. I tell you what, it was a isobar and the volume got smaller. I think it did this. But you don't add any weight, you don't take any weight off because it was isobaric on that last problem, whatever it was it 136E? Was that what it was? Ah, but see, when you get to that state 2, you had some liquid down here in the bottom. We'll put a little, there's some liquid. Yeah, you had vapor, all right. This was all vapor, wasn't it, to start with? And what was the heat transfer? Was it positive or negative on that problem we just did? Does anyone remember? I can't remember.
Negative.
Yeah, it was negative. So you had a heat transfer out. And, well, actually, I think it cooled off. It cooled off. It started off at, was it 200 degrees? Was it 200 Fahrenheit? I think it was 200 Fahrenheit. But what did it end up? Let me see what it ended up. I'm kind of curious. It ended up what was the pressure that it ended up at? On the wrong table here. Yeah, it ended up at 180 degrees Fahrenheit. It started off at 2. It cooled off. It cooled off. We never did do the device sketches. We did the PV diagram. But see, we're entering Wednesday, we're entering a whole new world. We're going to talk about things like turbines. See, with turbines, you have, it might be steam. It doesn't have to be steam. It can be a whole lot of different things. But you have some mass coming in and you got some mass going out. You don't have that with control masses. Whatever mass you got in here is the same mass. Now it might be liquid, part liquid, but it's the same mass. Oh gee, our time is about up. We've had a good time. But we're going to study turbines and nozzles. And let's see, turbines and nozzles and I don't know, heat exchangers, throttles. There's just a whole bunch of devices that have mass going in. Pipelines have mass going in and mass coming out. That's what we're going to study starting on Wednesday. You might want to read ahead a little bit, do your homework. Okay, it's been fun. I'm going to come over here where it says end everything. Do you have any last words? Here's your last chance. Speak now or forever hold your peace. We're going to say goodbye. Okay, goodbye till then.